Hi, Johnnie Hancock here. Welcome to the Keysight Oscilloscope webcast series. Today, our webcast is going to be on making power supply measurements using an oscilloscope. That's probably the instrument you use most often to characterize your switch mode power supplies. We're going to talk about a broad range of measurements, beginning with AC power quality, current harmonics, and then probably some of the ones that are most important to you is measuring losses, such as losses in your switching device, both power and energy, as well as output ripple. Now, we're also going to talk a whole lot about proper probing techniques. The only your measurements are only as good as how you probe them, which are really important, especially for output ripple. So you're welcome to view the whole webcast, or you can see time tags and subtitles down below. You can just click on them and just advance to the sections you're most interested. So let's go ahead and get into the agenda.
So the agenda, first of all, we'll give a quick overview of a switch mode power supply, talk about probe deskew, which is very important if you want accurate measurements, and then we'll get into three different categories: input measurements, switching measurements, and output measurements. Now, many people, they're not interested in completely characterizing from A to Z, from input to output. Sometimes they're zeroed in on the input side. Some folks are zeroed in on the output side. We're going to talk about all the measurements. We're going to wrap it up with some probing recommendations. So let's go ahead and get started here. First of all, when you consider power supply basics, the job description of a power supply is to efficiently produce well-regulated and low-noise DC power from an input rail. Now, there are two basic types of power supplies. There's linear power supplies and switching power supplies. Now, when I first started my career 36 years ago, almost all of the power supplies were linear type. And they have some advantages. And there's still linear power supplies out there today. In fact, many DC to DC converters are effectively linear power supplies. They have low noise, low filtering requirements. Some of the trade-offs, though, they're always step down in nature. They're inefficient. They're somewhat costly. And as far as a big linear power supply, they're big and heavy and bulky and can generate a lot of heat. A switch mode power supply, some of the advantages are they're highly efficient. You can get more power out of a smaller package. There's a variety of topologies. It's not just step down. You can get step up. But the big trade-off is they have moderate to high noise or output ripple. Now here we show a real basic simplified schematic of a switch mode power supply. On the input side, you typically have a full wave rectifier, so it's going to convert that AC input, which is typically line. It could be a lower type AC input, but typically line here in the U.S., 110 volt AC. In Europe, Asia, South America, often 220 volts. It's filtered, and then it goes through the heart of the switch mode power supply, which is that switching transistor there in the middle. And we'll get into that in more depth a little bit later. And ultimately, it's filtered again and rectified, and you have a DC output. Now, I've listed here some of the key measurements that we're going to be talking about today, some of the key measurements on the input analysis, AC input analysis. Now, some of these could apply to AC output if you're working with an inverter, and some of the switching device analysis, as well as the DC output analysis. So some of the trends in power supply design today, engineers, first of all, they want more efficient power supplies, green energy. People want to improve power density, pack more power into a small package, increase reliability, control EMI, improve output power rail integrity. That's extremely important today for high-speed digital designs. Decrease thermals, make it such that it doesn't run so hot, and reduce costs. Now, all of this adds up to increased test time, which is our focus today. So before you make any power supply type measurements, probably one of the most important things you need to do is deskew your voltage and current probes. So if you're making power measurements, it requires those two types of probes. Voltage times current equals power. The problem, though, is often your two different probes, there's a skew between them, and you need to skew that out. We offer a deskew fixture that you can use, and you can press a button and it automatically deskews them. If you see here, if I click on this, you see it's automatically deskewed. You can also create your own fixtures, simply a resistor and a wire, and connect your voltage probe across the resistor and your current probe, typically a clamp-on right near the resistor on the wire, and you can create your own fixture and manually deskew them. All scopes today, you go into the probe menu, have the ability to manually deskew them, line them up visually. Now, when I say all scopes, maybe I'm wrong. Maybe some of the lower-end scopes don't have that, but most of your mid-range and high-performance scopes have that ability. So let's take a look at input line analysis, AC analysis, and then we'll step through and looking at switching analysis and then DC output. There are three primary measurements that are performed to analyze the input power quality. Number one is power quality, things such as real power, or reactive power, apparent power, current harmonics, and inrush current. Let's take a look at the first one, power quality. So what I'm showing here is what we call a signals connection diagram on one of our Infinivision X series oscilloscopes. It gives you some hints on where to connect the probes, some suggestions for you if you're analyzing AC input in North America. It's 220 volts. You need a probe that can handle approximately 300 volts peak to peak, but if you're working with European or Asian power, up to 240 volts RMS, you're going to need a differential probe that can handle up to approximately 700 volts peak to peak. Current probes, typically for these type of measurements, it's a clamp-on type or Hall effect current probe. If you press the auto setup, the scope will automatically set up the voltage waveform and the current waveform and turn on the power waveform math function. Now, to give you some hints here, if you don't have an automated power option on your scopes, first of all, you need to scale your waveforms to near full screen to take advantage of all the bits that the scope has. I often get screenshots from our customers, and they're having problems with accuracy and resolution, and I find out they scaled the waveforms to 1 or 2 divisions. Well, if you scale the waveform, if you got 8 divisions peak to peak, and you scale, say, one of your waveforms to 2 divisions, now you're only using 1/4 of your A to D. Or if you got an 8-bit scope, now you've got a 6-bit measurement. So first of all, scale the waveforms near full screen. And then most scopes today have have waveform math, which is simply, if you want to power, you do channel 1 times channel 2. So here, the yellow waveform is voltage, and I've labeled it V sub I, or instantaneous voltage. The green waveform is current. One thing to note about this, with switching power supply, it's going to be pulsed like this. It's not going to be a sine wave. So the current comes out in pulses. And then the power is just simply computed V times I, the instantaneous power. If you press the apply button on our scopes, then it turns on a broad range of measurements to tell you about the input power quality. Let me click here. Okay, the first one, I don't know if you can read the values there or not. The real power, typically the symbol is P for power, is simply the mean or the average power over N cycles. Now, if you're doing this manually, our scopes, you're able to select an average over N cycles or the average over full screen. Some scopes don't have the N cycles. In that case, you need to gate that measurement and make sure the measurement is over a discrete or integer number of cycles. So this is the real power is really the only one that you can typically measure on any scope directly. All of the other measurements are derived from other parameters, such as apparent power is simply voltage RMS times current RMS, again, over an integer number of cycles. Scopes typically have the RMS, IRMS. The reactive power is computed by the square root of the apparent power squared minus the real power squared. Power factor is simply real power divided by apparent power. Phase angle is arc cosine real power over apparent power. And then CF stands for crest factor, is just a ratio of peak over RMS for both voltage and current. And so the real advantage here of having automated power app in your scope, whether it's from a Keysight scope or one of our competitors, is you get these things automatically so that you can get your answers much more quickly rather than automating it with a computer or using a pencil and paper. Another important measurement for line analysis is current harmonics. Now, I mentioned earlier that if you looked at the current, it was pulsed. You had a positive pulse and you had a negative pulse. It wasn't a sine wave. Back in the old linear power supply days, the current was a sine wave. Well, the problem with this pulse current that's characteristic of switching power supplies is it can inject harmonics back into the mains, and that can disturb other equipment on your mains network, power network. And so there are some standards that many different products must meet today. It's called the IEC 61000-3-2 specification. 3 different subclasses, Class A, B, C, and D. It really depends on the type of product that you're developing and ultimately selling to a customer. It must meet these standards. This was developed in Europe. And what you can see on screen right here is what the scope does is it runs an FFT measurement on the current waveform. And then what you can see in the top part of the screenshot there is a table. The first column just lists the harmonics. The second column lists the actual measurement of each harmonic. That's in voltage RMS. The third column lists the specification or the limits. And then we show the percent margin and then whether or not it's pass-fail. You can see in this example everything is passing. It measures up to the 40th harmonic. If it fails, you'll see a big red box and it'll say fail, and if it's marginal, it'll be in yellow. Now, there's 2 different ways you can view this information. What I'm showing right here is the tabular format. You can also select the bar chart format. And what I've evaluated on our competitors, they pretty much show the same thing. The last input line analysis measurement I'm going to show you here is Inrush current. This is a single shot measurement. You really don't need a power app to do this measurement. If you know how to run a scope, you can set up a single shot measurement yourself. With our power app, it sort of helps guide you along in setting it up, tells you when to turn off your power supply, when to turn it on, and so on. And when you initially turn on a power supply or a product, you turn on the power, there's going to be a surge of current because all of the input filtering on the input of the power supply, all the capacitance has been drained away, and all these capacitors initially look like a short circuit. So there's going to be an initial surge of current. In this case, I don't know if you can read the number or not. It measures a peak current of approximately 15 amps. And the scope will automatically measure the maximum or minimum peak current, whichever way it is. It could go either way. Just what you can observe here, the yellow waveform, again, is the input AC voltage. You can see it begin to ramp up, and then you can see the input current. We got the spike. We got a high level of oscillating current, and then it begins to settle down to more the steady state. Let's now take a look at switching device analysis. There are 4 measurements we're going to go through. Probably the one people are most interested in is switching losses. That's where a lot of the losses occur during power regulation. RDS on, slew rate, and then modulation analysis. Well, let's take a look at the theory of a switching power supply, and what I'm showing here is the theoretical or ideal world. You can see the yellow waveform is the voltage across the switching transistor. We call that VDS, or voltage drain to source, and the green waveform is IDS, or current drain to source. During the on state, that's where the voltage is 0 across the transistor. It's turned on. In the ideal world, the on-state losses are current times 0 volts, so you have 0 watts. During the off state, that's where current is 0 and voltage is high. Again, voltage times 0 is 0 watts. So the net losses in the perfect world is 0 watts. But let's take a look at the real world. Here we show during the on state, VDS is not 0. There's some small saturation voltage, and it's not easy to measure. And that's something one of my competitive colleagues talked about, and we're going to talk about that a little bit later, about the difficulty of measuring that actual voltage level. During the off state, if I can click on it right here, you may not measure 0 amps. Now, it will be 0 amps unless you have a problem with your switching transistor, but you may not measure 0 amps, and that's due to the current probe, typically the current probe or the scope null offset error. And then during the switching, when it turns on and turns off, the edge rates of these signals is not infinitely fast, and the transistor will pass through its linear region, and the net result is you will have, well, I clicked through that one a little bit too quickly. Let's go back through this real quick. You will have losses, most of the losses during the turn on and turn off time. You'll have false losses during the off state and conduction losses during the on state. Now let's take a look at, see what this looks like on an oscilloscope. Now first of all, let me explain, I scaled these waveforms wrong. I'm not taking advantage of the full resolution of my scope, but I scaled them this way so that we could see them more clearly. So the top waveform is VDS, the yellow waveform. The green waveform is IDS, current through the transistor, and the purple waveform is the waveform math function, which is volts times amps. So here we show the conduction phase of VDS. Here we show the non-conduction phase when current should be 0. And here where you see the pulses on the power waveform is what we call the TOFF time, or the time when it switches off. And the T-on, there is no pulse there. Depending upon the topology, there could be a pulse or a power loss during this phase. So let's now actually make a power loss measurement using the scope. The first thing I'd like to point out is this is the measurement that is probably most critical that your probes are de-skewed. Because if you just get a slight skew between your voltage and current probe, that's going to change the power losses during the turn on and turn off time. Another important thing is we mentioned earlier that measuring that saturation voltage across the switching transistor is very difficult. Our scopes have a precision offset calibration that can be performed, so this can really help improve the accuracy of making those measurements, and we're still going to talk about this more in a few minutes. You press the auto setup and the scope automatically scales 2 switching cycles across the main time base window and 1 switching cycle across the zoomed in window and turns on the power loss measurements. Now at this point, I don't know if you can read it or not, the power loss is measuring in a range of about 10.5 watts and an energy loss of 200 some odd, I think it's nanohenries, but I can't read it. At this point, you can zoom in and measure the losses of each of the phases, and we'll show that in a few minutes. Now the last thing I'd like to point out, I don't know if you can see it or not, notice how flat that power waveform is during the non-conduction phase. If you use the default settings on the Agilent InfiniVision X series oscilloscopes, we detect that that's the non-conduction phase, and we simply set the power to 0, because if it's not 0, what you're measuring is the scope and probe null error of the current probe. It should be 0. Now, if you can change that so that it actually does measure the error if you want to measure the error. But we go ahead and just clamp that at 0 watts. Another closely related measurement is measuring the effective resistance of your switching transistor. If it's a FET-type transistor, this is called RDS, or effective resistance drain to source, when it is turned on. What the scope does is it windows in on just the conduction phase, and it measures the average voltage and the average current during a window of time during that phase, and then it computes RDS as V average over I average. And again, it's important that you have done a very accurate calibration of the offset error prior to this measurement. Now at this point, once you've measured the RDS value, you can then select Use RDS to measure losses. If you click on that, then the scope switches back to the switching loss measurement, which we showed earlier and we're showing now. And at this point, it measures the losses based on RDS during the conduction phase as opposed to based on the actual voltage measurement. Now, if you look at the last bullet there, the one on the lower right, it actually computes the power differently in each phase of switching. And again, I think all scopes from our competitors, we do the same thing if you use the RDS factor. During the conduction phase, it's simply I square times RDS. During the turn on or turn off phase, it uses the conventional computation for power, and that's volts times amps. And during the non-conduction phase, again, as I mentioned previously, we clamp the current at 0, so it gives you 0 watts during the non-conduction phase. Now at this point, you can zoom in, and here I'm going to show how you can measure the losses during each phase. What I've done here is, using the zoom time base, I've zoomed in very accurately into in this case, the conduction phase. And I've also zoomed in vertically just on the power waveform so that we can see the slope of it. And there you can see the purple waveform is the instantaneous power equals the instantaneous current squared times the value of RDS on. In this example, I've zoomed in on the TOFF phase, and now it's using just V times I to measure the losses during this particular phase. Now let's talk about some of the measurement limitations. I've been saying it's very difficult to measure that saturation voltage during the conduction phase. There's a myth out there that the biggest component of error is oscilloscope measurement resolution. So many folks say, if I only had a scope at higher resolution, I could make this measurement much more accurately. Now, higher resolution is not bad, but that is not the highest component of error. The highest component of error is the scope or probe offset or position error. A typical specification for offset and position error on the scope and the probe, it's about 1/10 of a division, or you're looking somewhere around 1%. Now, if you're really good, typically a differential voltage probe is going to have a thumb wheel or a small screw adjustment that you can visually adjust and null out some of that error, but about the best you could possibly do is maybe half of this, about 0.05 divisions. So for example, let's assume that your error is 0.1 division. In this case, we show a volts peak to peak of our switching of nearly 300 volts, and the scope's volts per division set up on that voltage waveform is about 40 volts per division. And if the offset error is 1/10 of a division, then you're going to have absolute voltage offset of about plus or minus 4 volts, which is huge. The saturation voltage for a high power switching transistor, it can sometimes be well less than 1 volt. It can be hundreds of millivolts or even tens of millivolts. And even if you're really good and you can cal that out to 0.05 divisions, then you still have plus and minus 2 volts. So this is a big issue with trying to accurately measure the power losses during the conduction phase. My recommendation is to actually get the specification out of the device data sheet of what is RDS on, and here you can see one for a particular power transistor from Fairchild, and you can see it's a very low value. It ranges from 7.5 milliohms to 9 milliohms. You can, as earlier I showed, measuring RDS on and then using that value, you can also directly enter the value of RDS, and this is how you're going to get your most accurate measurements. Let's move on to another important measurement for switching devices, and that's slew rate. That determines how fast a device is going to turn on and turn off. If you can turn them on and turn them off faster, you're going to have lower losses, and we'll talk about what the trade-offs are of that. Now, there's a couple different ways you can measure it. What we do with our automated power app is we actually zoom in during that switching time, and we turn on a different math function this time, not V times I, but we turn on the differentiate, or dV/dt, if you're measuring the slew rate of the voltage waveform. And you can see that purple waveform at the very peak is where the maximum slew rate is, and I think we're measuring somewhere in the range of about 19 million volts per second on this particular device. People typically think of it as 19 volts per microsecond. Our scope just shows you the million volts, so you can flip that around if you want. Another way to measure this, you don't need the power app. Some scopes do this, is you can use the tracking cursors or markers on the scope. So you can set those two markers near where you visually think the highest slew rate is, and then in our readout we also, if it's tracking, it's measuring volts, delta volts, and delta time, we automatically show you what the slew rate is. And this next slide here, I just show you the slew rate of the current waveform. Again, it just uses a differentiate math function, dI/dt. The last measurement we're going to talk about for switching device is modulation. And what the scope uses for this is what it's doing is characterizing the control signal that's controlling the switching on, switching off, and that's the voltage level on the gate of the switching transistor. And we use a measurement called the measurement trend. And what a measurement trend is it's in this case we're doing a trend of the duty cycle of VGS, gate to source voltage, across that transistor. So on the vertical axis, on that purple waveform, is duty cycle. On the horizontal axis is time. And so if you look at the yellow waveform is VGS. There's some modulation going on there. I can't see it, but the trend waveform pulls it out. And in this case, I can see there's some what appears to be AC modulation. Now, there's various parameters you can select. In this case, I'm showing duty cycle. And here's an example of measuring the trend or the modulation of frequency of the gate signal. And in this case, I'm showing an example of what happens when you initially turn on the power. So you can see the voltage ramp up on the gate, and then but you can also see on the purple waveform the frequency ramps up, and I think it ramps up in about 400 microseconds until it gets to its steady state switching frequency, which in case this is from our demo board, it switches relatively slow, about 70 kilohertz switching rate. Now, some of the trade-offs for power device analysis, and by the way, I don't know if questions are coming in yet. I don't have that window open. I am not a power supply designer. I am an oscilloscope. Some people would say I'm an oscilloscope expert. So when you're throwing these questions at me, I appreciate if you throw measurement questions at me and don't ask me how to design a power supply, because I'm not a power supply designer. But these are some of the trade-offs they make. Switching power supplies, they're getting faster today, faster switching frequencies. And what the benefits of that is it allows for smaller inductive devices, which means you can get higher power density, more power in a smaller package. These smaller inductive devices have lower costs. But the trade-off is if you have a faster switching frequency, now the duty cycle of that turn on and turn off time when the losses occur, when the transistor is switching, that increases. Now, to resolve that, you could have faster slew rate devices. That's going to lower the turn-on, turn-off losses, because now that delta time when it's ramping up and ramping down is much smaller. But the big trade-off is higher output ripple, higher EMI, and of course higher cost with a faster switching device. And that makes some of the output analysis, which we're going to talk about more next, more important. So on output analysis, we're going to look at, real quickly, 5 different measurements: output ripple, turn on, turn off time, transient response, efficiency, and the last one here, power supply rejection ratio. So output ripple is actually a pretty simple measurement but there are some limitations and issues you need to be aware of. So here I'm showing, again, this is our connections diagram. You typically just connect a passive probe, most people do, to the output DC signal. Here you can see we're measuring a 15-volt DC supply. Output ripple is becoming more and more important today because any kind of ripple or noise, some people just call it noise, on the output DC signal, if it's trying to drive high-speed digital devices, the noise on the power rail is going to translate into jitter and timing uncertainty, and it's going to effectively close your data valid windows. So output ripple is becoming a more and more important issue, and it's often called power rail integrity measurements. Now, I mentioned here in the bullets here, there are many probing limitations. If you want to measure millivolts of noise, you're typically going to have to use a one-to-one probe to measure that low noise. So here I show pressing auto setup, and what the scope is going to do is going to AC couple that signal and then blow it up and simply measure the volts peak to peak as well as VRMS to give you a feel for what your output ripple is. Now let's talk about what some of the probing limitations are. Now I mentioned we recommend using a one-to-one probe for low millivolts. The problem with the 10-to-1 probe is going to limit the scope's input sensitivity on most scopes somewhere between 10 millivolts per division to 20 millivolts per division. So if you're trying to measure 2 millivolts, you're not going to be able to measure it very accurately. Another problem with the standard 10-to-1 probe is not only does it move your dynamic range up away from your most sensitive settings, it also expands your scope's noise floor by a factor of 10 as well. The problem with a one-to-one probe, you get your maximum sensitivity, so 1 millivolt, perhaps 2 or maybe 5 millivolts per division on your scope, but a one-to-one probe has limited bandwidth, approximately 35 megahertz. Also, the one-to-one probe is going to limit your DC offset range, and that's why, as I showed earlier, we AC couple to measure that ripple. Now, we've talked to a lot of our customers about this, and this is a big issue. They tell us, I want to measure the DC component at the same time as the AC component, or the ripple, and I want to be able to also measure any slow drift. Well, AC coupling is going to destroy the slow drift that you may want to measure, as well as the DC component. Now, you can always measure the DC component in a separate measurement, but it's that slow drift that's going to be destroyed. Now, let's talk a little bit about more probing techniques, and then I'll show you what we consider a very good solution for some of the issues I just presented here. And what I'm going to talk about right here is something that my competitive colleague really pointed out earlier. So here we show one of our passive probes and some of the accessories that ship with it. And this is the accessory most engineers and technicians use to connect the ground to their circuit. But that is also can be considered an inductor as well as an antenna. Now let's take a look at comparisons of measurements. Well, before we get to that, this is the best grounding technique. There are various accessories that you can get good short grounds. This is one that actually solders into the board, so it's not the most friendly, but if you can put in something like this on your board soldered in, you're going to get a very good short ground connection. Now I have 4 examples here. Here I'm measuring the output of a USB power. And in the first example here, I'm using a standard 10-to-1 probe, the probe that ships with the scope, and I'm using that long antenna to make that measurement. And in this case, you can see that we're measuring an output ripple of about 64 millivolts. In this example, I've removed my antenna, that ground lead, and I've used one of the grounding accessories that ships with the scope. It's a little spring clip that's got a very short ground, and you can see that I've reduced my output ripple in half. So I didn't really reduce my output ripple. I reduced what the scope is measuring. The next example, I'm using a 1-to-1 probe, again with my long antenna, and again I've reduced it again. Now I'm down to about 21 millivolts. And last, here's the best measurement I've performed. Now I've got it down to about 8 millivolts, again using a 1-to-1 probe and a ground clip. Now why is that noise so low? Part of it is good probing techniques using that ground clip. Another issue may be that I went from a 700 megahertz 10-to-1 probe down to a 35 megahertz 1-to-1 probe. This is what I just mentioned earlier, is a new solution we just introduced a few weeks ago, actually. We call it the N7020A Power Rail Probe. It allows people to measure output DC signal integrity with high bandwidth. It's an active probe. It's got 2 gigahertz bandwidth. It's a 1-to-1 probe, so you can take advantage of the maximum sensitivity of the scope. And it also has plus and minus 24 volts offset. So you can measure the DC component, the AC component, and slow drift all at the same time and without losing anything. Now here we show an example. This is on one of our Infinium Windows-based oscilloscopes. The orange waveform is using that 35 megahertz 1-to-1 probe. You can see it's noisier. The yellow waveform is using the new power rail probe. You may not be able to see it, but there are some very narrow spikes in there that have very high frequency. That's what the 1-to-1 probe is going to miss. Plus, there's much lower noise on this. There's a webcast that was presented, it was a month or so ago, by one of my colleagues at Keysight. It's called Measuring Power Rail Signal Integrity with Oscilloscopes. Now, I've listed a URL here that you can go to if you want to view that webcast. It talks specifically about this issue. The whole webcast is on power rail issues. Another measurement for output analysis is turn on and turn off time. Again, you don't need a special power app on your scope to do this. If you know how to run a scope, it's basically a single shot measurement. So the top waveform there, I'm showing turn on time. So when you turn on your product or your power supply, the DC is going to ramp up. What's nice about the power app is it automatically measures from the initial turn-on time that it detects an edge crossing on the AC input until it reaches 90% of the expected value. In this case, I believe it was a 12-volt power supply. And then the turn-off time automatically measures the time from when the AC goes away until the DC decays to the 10% level. If you don't have the automatic power app, you probably have to just simply use your oscilloscope timing cursors, manually set them where you visually want them. Another important measurement is transient response analysis. What that is, what I'm showing in the upper screenshot there is one of our help menus. If you press and hold down a key, it's going to pop up a help screen and explain the measurement for you. When you initially change a load on the output of your device under test, there's going to be a transient that will occur on the DC that's driving it. So if you have a sudden increase in load, that means the current is going to go up. There will be a sudden decrease in the output voltage until it can re-regulate it and get it back up to where it needs to be. So what we're showing here on the lower waveform, the green is the current. You can see it going from a low level, stepping up to a high level. The yellow waveform is the voltage. You can see, as I just mentioned, it will take an immediate dip and then come back up and settle to its output level. So we're zoomed way in there on that DC voltage. And the scope automatically measures from the initial time it goes out a percentage setting that you can set until the last time it comes back to within that tolerance setting that you have told the scope to measure to. Now, the last measurement people often think about making, and perhaps it's the most important, is what is the efficiency of my power supply. There's multiple ways you can do this. You can take the measurements, the very first measurement we talked about where we measured input power quality. It will measure real power for you. Then you could take a standard multimeter and measure the DC output, both voltage and current, and then just compute efficiency. You can also automatically do it with a scope. However, it's going to require two current probes, one on the input and one on the output. Our particular app, it allows you to measure the efficiency of AC to DC, which is most typical for a switching power supply, as well as AC to AC, DC to AC, and DC to DC. So it's a pretty simple measurement. Input real power divided by, let me back that up. Output real power divided by input real power, and then it's measured in percent. Now, the last measurement we're going to talk about here today is power supply rejection ratio, often termed PSRR. Now, this is a measurement you don't typically think that can be measured on an oscilloscope. So power supply rejection ratio, some people call it power supply ripple rejection. What it is it provides a measure of how well a device, such as a DC to DC converter, a linear voltage regulator, or LDO, how well does it reject various frequency components at the DC input. And so if you have, rather than noise, input noise is broadband, some of that is going to sneak from the input to the output. This allows you to inject a known frequency and measure what is getting from the input and the output. And the way power supply rejection ratio is computed, it's 20 log Vin over Vout. Now, some people argue, no, it should be Vout over Vin. That's actually 20 log Vout over Vin is gain. This is rejection, so it's Dn over Vout. Now, what it requires a disturbance signal or a source. Our InfiniVision X series oscilloscopes have a built-in function and arbitrary waveform generator. You can use that as the disturbance source, but it also has to be summed with the DC input. You can't just directly connect the function generator to the DC source. It has to go through a summing network, and one here that I recommend is from a company called Picotest. This is the Picotest J2120 line injector. Other alternatives, you could couple with inductors and capacitors each of those sources, the DC source and the AC source, but you'd have a very limited frequency band. You could also design your own unity gain amplifier to stick in there. The easiest thing is just to get one of these boxes from Picotest and stick it in there, and so it's got an AC input and a DC input, and it's got a single output. So let's take a look at the measurement on the scope, the PSRR measurement. So first of all, you connect your waveform generator output to this line injector, your summing network, and then also you connect your probes up to measure Vin and Vout. Now, we recommend that for measuring Vout, again, you use a one-to-one passive probe, because if you've got a lot of rejection on your converter that you're running the test on, the output voltage level is going to be extremely low, and that's one of the limitations of using a scope for this measurement. Typically, you use a network analyzer. And then you can enter your frequency range you want to test from. We're able to test up to 20 megahertz. You enter vertical plot scaling and then enter the amplitude of the test signal that you want to use for your disturbance. What is the AC value, peak to peak, of the AC disturbance signal? Before I show the final measurement, here, this particular screenshot, I'm showing the measurement at one particular frequency. I believe this was 10 kilohertz. Now, you probably can't read some of the scale factors here, but the channel 1, that's the yellow waveform, that's Vn of the disturbance signal, and the scope is set up at 100 millivolts per division. So this is about a half a volt peak-to-peak input. Channel 2 is at 1 millivolt per division, and that's the green waveform, that's Vout. And so in this case, you can see we're measuring about 1/4 of a millivolt, or 250 microvolts. That is not easy to do on an oscilloscope. And what the scope does, in order to dig that waveform out of the noise floor of the scope itself, we use averaging to eliminate all non-correlated signals such as random noise from the scope, and we also bandwidth limit to 20 megahertz. And then the scope steps in multiple frequencies from the low frequency setting to the high frequency setting, and then it measures VRMS of input and output, and then it computes the PSRR 20 log VN over VOut, and then plots the results. So here you can see the completed measurement. It just does it one time. It takes approximately 1 minute to do this sweep. The common thought I've heard about what's the best a scope could do, they say about 50 dB, and that may be true if you're not using averaging or some of the techniques we use here. I've been able to measure, in this case here, I'm showing about 74 dB of rejection, I think around 20 kilohertz in this example. But I would say the maximum dynamic range is about 70 dB. So the bottom line, this is what I've been calling a poor man's vector network analyzer. This doesn't replace a network analyzer. A network analyzer would do a far better job, has much more dynamic range than an oscilloscope. But if this is good enough for you, it's a pretty simple and inexpensive solution. So let's review what we've learned today. Power supply design optimization requires lots of testing and characterization. The point I've been trying to make here today, oscilloscope licensed options for customized power measurements, it can decrease your time to test. We believe the power options available on our oscilloscope provide the most comprehensive portfolio of power-related measurements. Our power measurements provide setup diagrams, step-by-step instructions, help screens, and so on to make some of these measurements that can be pretty difficult a lot easier. Also, probing and grounding techniques are extremely important if you're trying to get accurate measurements. And Keysight offers a wide range of voltage and current probes to meet your needs. These are some of the recommended probes for power supply characterization. I certainly didn't list all of our probes. The ones I have highlighted there in blue are some of the more popular probes for power supply characterization. For a high voltage differential probe, you can see the one listed there in 2790A up to 1400 volts. There's an error on this. It says 50 to 1 or 100 to 1. That's actually a 50 to 1 or 500 to 1 to get that 1400 volt range. And down at the bottom you can see this new power rail probe listed there. And again, this is not a general purpose probe for other applications. It's specifically a power rail probe for measuring ripple on DC. Keysight has a broad range of oscilloscopes, ranging from handheld scopes, the U60, 1600, all the way up to very high frequency, ultra-high frequency bandwidths up to 63 gigahertz. The scopes primarily I focused on today are the ones you can see highlighted there in green, the Infinivision series. We have 4 different main products in that series, the 2000, 3000, 4000, and 6000 X series. Various bandwidths as well as sample rates. The 2000 series does not have the automated power app, but all of the others do. I also showed one measurement on the Infinium. This is our new Infinium S series. It has a very low noise front end and 10-bit A to D. This is an extremely good solution along with that power rail probe to measure power rail integrity. Now that power rail probe is also compatible with the Infinivision X series as well. We have a lot of technical resources available. You can go to Keysight's website and find some of this information. I think the one I would recommend first might be that switch mode power supply measurements application note. It goes through a lot of the measurements I talked about today. It's still, you can see I've got a picture of that app note there. It hasn't been updated for Keysight yet. It still has that Agilent spark on there. So at this time, I think I'd like to turn it back over to Bill and open it up for Q&A.
Here's the first one. Are these probes for the AC current all compatible with other scope manufacturers?
Some of them are. Some of our probes have what we call the auto probe interface, and that's a Keysight auto probe interface. And in those cases, those probes can't be used. But also some of our probes have a standard B and C connection. And some of them have battery operation or an external power supply. Those particular probes can be used on any vendor scope.
Okay, here's one more specific. Is the 720 scope probe compatible with the Tektronix scopes?
Unfortunately not.
Okay. What are the low and high frequency step points for the PSRR sweep?
I believe the low point is 10 hertz. The highest frequency is 20 megahertz. That's the maximum bandwidth of the built-in generator on these scopes.
Okay. Do you know which scopes offer WaveGen?
All of the InfiniVision X series, so the 2000X, 3000X, 4000X, and 6000X. The 4000 and 6000X offer 2 output channels and also double the output drive capability. Although for a PSRR measurement, you don't need high output drive. You're typically disturbing with a very low output signal.
Okay. How do you effectively measure the current in milliamps using a current probe? I know you have to calibrate it to measure in the range of 10 to 100 milliamps. Even after reducing the offset and calibrating the probe, I can still see some noise on that measurement.
It's a challenge trying to measure low milliamps or even microamps. First of all, you talk about calibrating the probe. This is something I didn't mention. One of my competitive colleagues really hit on this a few months ago. There's a degauss button. So probes will build up a magnetic element on them, and they will drift and build up a DC offset. And you have to continually degauss them and then recalibrate the DC offset. Now, if you're trying to measure low milliamps and sub-milliamps, a typical clamp-on current probe is not the best solution. There are other techniques using sense resistors, a sense resistor technique, which is basically what a multimeter does to measure current. You can use your own. You can put in a small resistor in the circuit, making sure that the value of the resistance does not substantially affect the operation of the circuit. So it could be something like 100 milliohms, and then measure the voltage across that and convert that to current. We also have a probe we introduced about a year ago that is automatically made for this. It has a sense resistor technology, and also you can embed these connectors on your board, and then you can plug in the probe, and it's got a make before break technology such that you don't have to break the line. If the probe's not plugged in, the line is made. Once you plug the probe in, it switches in that sense resistor before it breaks the circuit, and so you can continue operation. Another unique thing about this particular current probe, at this point I can't off the top of my head recall the model number of it. It also has dual outputs, and it's an ideal probe for measuring low drain current, for such as mobile devices. So you take an example such as your cell phone. You got it sitting there turned off. I've got it sitting in front of me. It's always draining a little bit of current and then it wakes up every once in a while and pops its head up and says, "Hey, is anybody out there? Do I have any calls coming in?" And then it goes back to sleep. Well, the difference in the dynamic range can be huge. And so when it wakes up, it's measuring a relatively high current. Then it goes back to sleep. It's still activity there. The problem is you can't measure both at the same time. This particular probe has two outputs, one that is high sensitivity that clamps, so you can measure down in the tens and hundreds of microamps range, and then another output side that has a higher current setting.
Okay. Do the input line analysis tools work on the DC input line?
Input line analysis tools. I don't think so. So if you wanted to measure, you could use the efficiency measurement. Well, automatically measure DC line input. It'll measure the real power. But you can't use the AC line analysis on a DC input. Current harmonics are, I suppose you could do the current harmonics, although it should be pretty low.
For the next question, it would be nice to know which probes are compatible with other scope makers. I'm not sure if there are a particular collection that would be.
The best way to do that is go to our website, take a look at the probes we have, and you can look at the picture, or I think we typically say, does it have the Keysight auto probe interface? And you can just look at the probe itself, and it's got a big fat input that plugs into the BNC. Or if the probe looks like a BNC connection, then that is compatible with other vendors' scopes.
Okay. The next question we have, for measuring AC noise on a rail, should you limit the scope's BW?
Bandwidth.
Bandwidth, that's what it is. They want to see higher noise content on the rail. Or they don't want to see higher noise content on the rail.
Well, that depends on what you're looking for. You can, if you're only interested in noise up to a certain bandwidth, yes, you can limit the bandwidth. The Infinium S-series scopes has several bandwidth limits that you can set all the way down in hardware, I believe all the way down to 20 megahertz. So there's a 20 megahertz selection, 100 megahertz selection, and off the top of my head, I can't remember where all the other selections are. And if one of the hardware selections doesn't work for you, we have a waveform math function for a low-pass filter, and there you can select any bandwidth you want to limit your bandwidth. Now, if you're trying to measure the highest frequency possible coupling or noise, or perhaps switching noise that's in there, you may want to open it up all the way so that you can see your highest frequency. Now, something I didn't mention is, we talk about a switching frequency in the case of our demo board that we use for some of our hands-on workshops. It's only switching at 70 kilohertz. But if you run an FFT on that, you're going to see you have multiple harmonics of that 70 kilohertz that go up to much higher frequency. So there can be frequency content due to the switching that's going on far beyond the actual switching rate.
Okay. Here's another one. How do you measure the ground difference on the scope? For example, you have the gate driver on digital ground and the driver MOSFETs are on power ground. How would you measure it effectively? I've used differential probes to measure ground difference.
I think you could do that. So if you have isolated sides of your power supply, so they're isolated, you could put a differential probe between them to measure what the difference in ground is, and just realize that the differential probe does have an input impedance, so it's not galvanically isolated, so it does connect a big resistor. It could be 10 megohms between one side and the other, so I think that would be one technique, but that's something I haven't done, not that familiar with it. So.
Okay. Does Keysight sell the Picotest accessory that you showed earlier for injecting the AC distribution signal for the PSRR test?
No, we don't. And in fact, our vector network analyzers also recommend some of the Picotest accessories. The best way to get some of those, if you're interested in, is just go to their website, and it's simply picotest.com.
Okay. Are there any alternatives to measuring current other than the traditional clamp-on current probes?
Well, I think I covered that a little bit earlier. Basically, using sense resistor technology, either come up with your own sense resistors, or as I mentioned, we also have that new probe. I think we introduced it about a year ago that has sense resistor technology.
Okay, I think you sort of mentioned some of this. Can your new power rail probe be used with the PSRR measurement?
Not today. We just introduced this power rail probe. Today I recommend using a one-to-one probe, which limits the bandwidth, but it's a relatively low bandwidth measurement anyway. The power rail probe, the advantage, if we were to use it for the power supply rejection ratio, the advantage is that it would have, you could use it drives into 50 ohms, which 50 ohms on the scope typically has a lower noise floor, and so it's going to give you more accuracy. And then also a couple of our scopes, like the 6000 series, has even a lower noise floor into the 50 ohms. So it might make making those low-level output measurements better. But today it is not compatible. Perhaps in the future we may enhance the product to include this new power rail probe for that particular measurement.
Okay. We're running a little over here, so this will be the last question. What bandwidth scope is required for switching power supply measurements?
My advice here, well, first of all, switching rates are getting faster. So the slew rates of many of your power devices are getting faster and faster, which requires higher bandwidth, and it's a challenge for all scope vendors to keep up with those requirements. About the highest bandwidth available today in a high voltage differential probe that will cover in the range of 1,000 volts is about 200 megahertz. And so right there, you've limited the measurement bandwidth of your system to the bandwidth of the probe. So it doesn't make a whole lot of sense getting a multi-gigahertz scope to measure something with a couple hundred megahertz probe. Now that's talking about specifically doing the switching analysis. Now, as we talked earlier about the power rail measurements, that's a 2 gigahertz probe, so you could get 2 gigahertz or higher scope to make those type of measurements if you're trying to look at extreme power integrity in a high-speed digital system.
All right. Well, that concludes today's presentation.